Thank you very much. Ladies and gentlemen, this is always a difficult time right after lunch, I know that. First of all, I really want to thank the Hellenic Copper Development Institute for putting together this very interesting breakthrough meeting and to inviting us all over to talk to you. And my talk will be about the mechanism of resistance to copper surfaces and to copper ions in the gut bacterium Escherichia coli. So there will be two halves of my talk. First, I will talk about the interaction of this bacterium with copper cations, because as far as we know, only bacterial resistance to copper cations is known. And when we talk about to fight resistance to antibiotics by using copper, of course we have to talk about copper resistance and the influence of copper resistance on survival of the bacteria on copper surfaces. And then in the second part we will switch gears and I talk about killing of E. coli on copper surfaces and possible mechanisms behind the killing process. So let's start with the copper cations. Well, most of the cations of the first transition period are important trace elements for the cells, and the cations of the second and third transition periods are toxic-only metals. Nevertheless, all of these cations are toxic to the cells, and to have any beneficial or toxic effect to the cells, they have to be transported into the cell. And E. coli is a gram-negative bacterium, so this transport has to be across two membranes. Here's the outer membrane, which tends to form blobs. The cytoplasmic or inner membrane, the space in between is called the periplasm, and the thin line in the middle of the periplasm is a Morian sacculus. So the cations have to be transported across a complete bacterial cell wall. We are still ignorant about uptake of copper-2 into cells of E. coli. Here's outer membrane, CPM, and cytoplasm. All we know is that copper-2 provided to the growth medium ends up as copper-1 in the cytoplasm. There is probably facilitated diffusion through the porine molecules, huge holes in the outer membrane, and OMC is likely to be involved. There is maybe first reduction from copper-2 to copper-1, and there is probably uptake by some unknown system which unspecifically imports copper-1 into the cytoplasm. And we are also still ignorant about any copper-dependent enzymes in E. coli in the cytoplasm. As far as we know, all the copper-dependent enzymes are in the periplasm or are located in the cytoplasmic membrane and extend into the periplasm. So as far as we know, there is no real need for copper-1 to enter the cytoplasm of E. coli. The only copper-binding protein known in E. coli is a regulatory protein called QER. And QER is a regulatory protein involved in gene expression control of the two genes QEO and COP-A. COP-A is a such-called P-type ATPase. It's an efflux system which transports copper-1 back into the periplasm. COP-A is in fact member of a huge superfamily of membrane-bound uptake on import proteins, and depending on the protein, the substrates are mostly inorganic cations from the small proton to the big huge lead cation, and they are all energized by ATP hydrolysis, and during the catalytic cycle a phosphorylated intermediate is being formed. And we know a lot about the function of this molecular machine by the work of the Tsuda group about the calcium P-type ATPase, which is needed in your process of muscle flasking. Now there is one family of P-type ATPases which has a conserved proline residue flanked by at least one cysteine, and these enzymes transport heavy metal cations, and there are two clusters, one for the divalent metal cations and one for the monovalent cations like copper and silver. And the ortholog of this family is the COP-A protein in E. coli. And in man, we have two orthologs, two homologs, which are involved in the Menkes and the Wilson's disease So there is also a copper homeostasis disease, at least 2 diseases in man. Now, when copper 1 has been exported to the periplasm, QEO kicks in, and this is a copper-dependent, molecular oxygen-dependent copper oxidase, which reoxidizes copper 1 back to copper 2. So we have one regulatory circuit controlled by QER, which controls the cytoplasmic copper content in a flow equilibrium between the unknown uptake route and COP-A-mediated efflux plus QEO-mediated reoxidation. And there is a second circuit which controls now the periplasmic copper concentration in E. coli. The membrane-bound histidine kinase Cas senses periplasmic copper and transmits the signal via phosphorylation to Cas-R, which is in control of the Cas determinant. And the main product of Cas is the Cas-CBA transenvelope. I call it a transenvelope gun. It's a huge complex spanning the complete cell wall, and this complex is involved in transport of copper through across the outer membrane back to the outside. We know a lot about these RND-driven systems. There are families which are involved in multiple drug resistance. They transport organic cations. Some are involved in heavy metal resistance. And they are composed of 3 different components, and they are driven by the proton motive force. There's a small additional protein which catches periplasmic copper in E. coli and delivers it into the Cas-CBA efflux gun, but this has an auxiliary function. So just to show you the contribution of this chromosomally encoded copper resistance systems in E. coli to copper resistance, here are some mutation studies, and please read this small 2 as a delta for genetically deletion. This is the transmission from MAC to DOS result. So these are the wild type. These are mutations in only 1 gene, double mutations and triple mutations. And we measured resistance to copper cations as a minimal inhibitory concentration on solid medium, which is the smallest concentration needed to block growth completely. And as you can see, deleting one of the 3 genes or gene systems, only COP-A deletion leads to a decrease of copper resistance by 1/3. Deletion of QEO or Cas doesn't change very much. Now, if you take the COP-A mutant and additionally delete QEO and Cas, then you see that resistance does not decrease further on. But when you now look at the triple mutant strain, where all 3 systems have been deleted, you see resistance compared to the wild type has decreased by another 1/3. And when you compare now triple and double mutant strain, where only COP-A is present, again, this doesn't change very much. So the message from this, COP-A is the most important factor because it is the only factor in E. coli which is known to detoxify the cytoplasm. But alone it's helpless. It needs QEO or Cas because these 2 systems complement each other in detoxifying the periplasm. And the copper concentration in the periplasm, of course, rules the copper concentration in the inside. So we have cytoplasmic detoxification and periplasmic detoxification either by Cas or by QEO. And there is an additional system which is where the genes are located on a plasmid. It's called the PCO system, and I don't want to go into much detail. Most of the products of the PCO system are also acting in the bacterial periplasm. Now let's move on to metallic copper surfaces. And we got interested in the work previously published by Kiewel and others, and decided to dig into the mechanism behind this killing process. And we changed the protocol. We used the similar coupons as Bill Kiewel has shown, and we changed the copper protocol a little bit. We are using cotton swabs and put some bacteria on the cotton swabs, a definite number, and then we smear them on the coupons so that we are in very tight control of the drying process, which led to a lot of experimental variations when we repeated the other protocol. And in the presence of nearly pure copper, you can see that with our protocol, killing happens within a minute. So the bugs are dead, and here is a control in steel which continues for minutes, hours, and even days. So it has now been published by a couple of labs that copper is indeed killing bacteria. So what's behind this process? You can see that there are 3 curves on top of each other because these 3 curves are wild-type strain. Wild-type strain with the deletion of the 3 chromosomally encoded copper resistance systems I've just introduced to you, so Cas, Q, Yo, and Cob-A, and wild-type, which additionally has a PCO resistance system. So we spread at the time a little bit by reducing the copper content of the surface by using copper nickel instead of copper. And now you can see quite clearly that wild type is now dead after 5 minutes, and the triple mutant strain is dead after only 1 minute. So there is a very clear contribution of the copper cation resistance systems to survival of the bacteria on the surface of metallic copper. And this is wild type with PCO. You do not see anything in this setting. However, when you pre-incubate the cells in the presence of copper cations, it's an induction process. Now you can see here is wild type, it survives a little bit longer. The triple mutant survives also a little bit longer, but there is still a huge difference. And this is now wild type, which additionally has a PCO metal resistance determinant. So this shows quite clearly that copper cations are involved in the killing process. And it shows that the copper resistance, which is of course a 2 or something billion-year-old trait, protects the cells a little bit against killing on copper surfaces, but protection is not complete. They are killed nevertheless. So we look a little bit closer into responsibility of the cations by adding complexing agents to the cell suspension before they restrict them out on copper surface, EDTA and BCS, and did the same experiment on nearly pure copper. And orange is control. You can see the cells are down to 1 per mil survivors in all 3 experiments, but after 15 seconds longer, the cells without complexing agents are dead, no longer culturable, but in the presence of these complexing agents which catch away copper 2 and copper 1, they survive a little bit longer. And the 20 millimolar concentration was absolutely at the edge of the concentration needed. Lower concentrations like 10 or 5 millimolar did not protect the bacteria. So by doing a similar experiment, we looked more closely into other components which might protect bacteria against the killing process. It's the same experiment. This is again the control, and you can see that after 1 minute the control again is gone, the bacteria are dead, but mannitol protects, catalase protects, superoxide dismutase protects, and also sucrose, whereas a substance called tyrone is even worse than in the control cells. So all these substances are interacting with reactive oxygen species. So superoxide dismutase is an enzyme destroying superoxide radicals. Catalase destroys hydrogen peroxide, and mannitol, besides a copper complexing activity, should interfere with hydrogen hydroxyl radicals. So we think from these results that under anaerobic conditions, there is some contribution of reactive oxygen species to the killing process. And this is most likely because in the presence of these reactive oxygen species, copper is cycling between the 2 oxidation states, copper 1 and copper 2, and is busily producing hydroxyl radicals, which are very toxic to the cells and which if it happens in the periplasm, is rapidly destroying the cytoplasmic membrane as a result of this Fenton reaction. There is a question, what happens when we take away the oxygen? Not very much. The cells are killed on pure copper within a minute in the presence of oxygen, but in Hungate tubes, in the absence of oxygen, they survive a little bit longer, but they are killed nevertheless. So what we think, also from a number of other experiments, however, is that when we take away the molecular oxygen, we inhibit the action of QEO, which oxidizes copper 1 back to copper 2. And we've seen from other experiments and also from a publication of Tom O'Halloran's group that under these circumstances is now the CAS CBA efflux gun is the only remaining system which is able to detoxify the periplasm and becomes very important. When the CAS CBA export activity has been overwhelmed, however, we could see with another experiment that we get a futile cycle. Copper 1 exported by COP-A is obviously being immediately re-imported into the cytoplasm and so on, so that the cells are no longer able to prevent a high copper 1 concentration in the cytoplasm under anaerobic conditions. And this may lead to the killing process. Under oxic conditions, however, we have copper 2, we have reactive oxygen species, which originate from the respiratory chain, and then we get Fenton reaction in the periplasm and killing of the bacteria. So at least in the lab, with coupons and a very strict protocol which has to be absolutely used, under these circumstances, E. coli is sitting between a rock and a hard place, and the bacterium is killed if oxygen is present or not, if interfering agents are present or not. So what's happening in the hospital? We are in the middle of a trial with the Asklepios Hospital in Hamburg in a cooperation, and we used a station and exchanged in 50% of the pushing plates, of the doorknobs, and of the light switches. And then we analyzed the copper content of the bacteria in 16 samplings. We did this in the summertime, the results are ready, and we had just started on the second round of sampling during wintertime. And overall, we did not get the same result as in the lab. We did not get the same result as has been described an hour ago by Professor Elliott. However, we got a significant decrease. I don't like the expression reduction when I talk about copper. We don't get a decrease. We got a significant decrease of the colony-forming units on the surfaces by 33%. And something else, this is an experiment, repopulation experiment. So we used pushing plates and sampled the colony-forming units. This is done several times, and you can see this is on copper, and this is on standard surfaces, so that 1/3 of difference. Then we cleaned them, and you can see the number of germs decreases, and then we measured after 3, 6, and 9 hours repopulation of the surfaces, and you can see quite clearly that repopulation of the copper surface is much slower compared to repopulation of the standard medium. So let's sum this up. The first part, we're still ignorant about the uptake routes of cations, copper cations into E. coli, and we do not know if E. coli needs a cytoplasmic copper-containing enzyme. It needs periplasmic copper-containing enzymes, but no cytoplasmic enzymes are known. The cytoplasm is detoxified by COP-A, and the first regulatory circuit, the detoxification either by CAS, the efflux gun, or the oxidase QEO. And there are 2 regulatory circuits controlling the expression level of these detoxification systems, and they control copper homeostasis in E. coli. When we streak them out on copper surfaces, they are dead within a minute. We can spread it by using an alloy with a lower concentration. And all the copper-resistant systems, or more exactly, copper-cation resistance, which Mother Nature has evolved during the last 2 billion years to protect against copper cations. They protect the cells also on copper surfaces, but protection is not complete. They are killed nevertheless. We can protect the cells by chelating the substances or by adding substances which interfere with reactive oxygen species. There was a result with tyrant, which I do not understand, anaerobiosis also, but nevertheless, the cells are killed by copper, which is mainly an interaction between copper cations plus reactive oxygen species. So thanks again, the copper surface work was done by a student from Portugal in our lab, Christoph Espirito Santo. So we are really working in the European community. And most of the guidance was done by Gregor Grass, who is now in the United States. My daughter was for 2 days in the lab. And this was the first time, it's beginner's luck, that we saw any difference between cells having copper-resistant system and not. And as a proud father, of course, I have her here. So they did nearly nothing. And after visiting my lab, she decided against biology. So, and people who are giving us the money, and of course, Dr. Klassert and the German Copper Institute and the International Copper Association for their contribution. And I thank you for your attention. Thank you very much.
Good afternoon, ladies and gentlemen. I'm very pleased to be invited to participate in this conference. I'm an architect, and for all of my professional life, I've been working in the health sector, sometimes as doing research, sometimes designing, and sometimes advising. And I'm obviously moving on to a different perspective of the topic. The real problems of HAIs has been clearly identified for us today. The fact that there seems to be an amazing way of solving and improving the situation by copper has also been very, very clearly identified for us. So what I want to do, though, is just tell you what the sort of climate is in terms of our designs of hospitals in the UK, which is the climate into which we want to put something new, something different. Now, I've always been very interested on the impact between, or the relationship between the buildings, the hospital buildings, and the clinical and other therapeutic activities that go on in them. But in particular, a few years ago, we were given a small piece of work to do for the NHS, to write something on designing to reduce hospital-acquired infections. And I have to say I prefer the term hospital-acquired infections because that's more accurate than the rather softer thing of health-associated infections. Anyway, we then got very involved in this particular area, and it is something that I spend quite a lot of time being interested in. Now, what I wanted to say first of all, because I was asked to give a little picture of what it's like, what the principles are in England for designing hospitals. Now, there are some key design principles which are now acknowledged, accepted, and being implemented. And one of those is to provide amenities for patients and visitors. One is to provide attractive interiors, and for buildings to look welcoming and friendly. Now, those requirements have actually come from a lot of discussions and meetings with patients and the public, particularly the public. And the government's response was to pick up these issues. And it is quite interesting that very, very quickly the designers have responded almost immediately to do different interiors. On this, I'm just going to show you a few images. I won't talk about them particularly. But what's interesting is that pretty well everywhere, whether you're talking about Scotland, you're talking about south of England, you're talking about London, you're talking about Northern Ireland, there is now this incredible focus on trying to design the interiors to be different. Just say the image of the windows is to do with people not being shut inside, to feel there's an inside-outside relationship, which is deemed to be very important. The other thing that was complained about, amazingly, was the smell of hospitals. How this is a waiting room, attractive, comfortable. But it raises the question, which is that usually we rely to some extent on environments telling people or helping people to know how they should be behaving in them. And I think it's a very interesting issue which we haven't really explored as to whether people's behaviour is as appropriate for a hospital or a clinical setting because of the way these are presented now. They are presented to look like hotels, like something rather exciting, like something very relaxed. And actually, it is, as we know, it's a location where you can't afford to be relaxed. You need to be extremely aware of a lot of things. And one of the reasons I've put this particular image in is because when we talk about introducing new things into our building designs, they need to be compatible with the designs that are currently being built. It's no good having something that is a piece of furniture or piece of equipment or piece of ironmongery that actually was appropriate 20 years ago, 50 years ago, perhaps even 10 years ago, because now the buildings that they're going into just have different design bases completely. Now, another major issue was to provide therapeutic environments. And that is based on the premise that reducing stress levels in patients improves their recovery rates. And that is the basis for all these things. And so now there is emphasis on views from windows, access to gardens, privacy, lack of noise, artworks, lots of artworks, colours. People hated what they called the hospital green. Patients having some control over their immediate environment. Now, it's very interesting because actually, if I'm speaking for myself, I feel I would be much less stressed if I thought the risk of getting one of these infections was reduced rather than thinking that I was being exposed to them. And that would be exactly the same if I were the patient or if it was my relatives. So I think this issue of what reduces stress is worth just looking at a bit more strongly. But certainly, personally, I would rather know the risk of getting MRSA was reduced. It would make me feel darn sight better. Again, we're talking about corridors that people didn't like, so now there are corridors that have got windows, not usually, they try to have windows so that people can look outside. And then, of course, there is a choice of different environments. Getting people outside for children, it's very nice. The next one is really nothing special about these, but it's just emphasis that somehow in the last, I suppose, 8 years, the importance of putting artworks all throughout the hospitals and all the health buildings has been picked up by the public, by the patients, and by the staff, amazingly. And of course, it does just raise the question of whether there could be some copper works of art around the hospitals, which might actually serve a double function. And again, a lovely view from a waiting room, which is pretty attractive and very relaxing. Now, when we're looking to the future, there have been 3 requirements that have been coming in for all the briefs, and that is to introduce innovation. Now, introducing innovation is the thing that we're extremely bad at. We're good at repeating, we're really pretty lousy at innovating. There's innovation in terms of what the clinical activities are. There's actually some very interesting, of course, new pieces of equipment that allow a great many deal of examinations and analysis to be done that couldn't be done before. But innovation of building has really not happened very often. I have one example that I'll show you. The next thing, of course, is achieving high levels of sustainability. Well, another plus for copper, because of course that is 100% reusable, and they haven't put that on the tick list yet, but it may get there. And then building hospitals that can accommodate future changes and developments. And these are the design principles that have come down from the Department of Health's guidance, really, but based on mostly on interviews with people, with the public. I've put this one in because this is really, truly the only one that I can think of that is a real innovation that we've had, and this is a barn theatre, which is when you have a whole number of operations going on simultaneously. Now, the benefits of this had been shown and demonstrated in other countries, and the fight that hospital had to get it was really unbelievable. And it got to the point where the surgeons who were sure it was the right thing for them and for their hospital, the top surgeons, they actually had to make a tremendous fight. And finally they got it. And of course now the hospital is terribly proud of it. Lots of people come to see it. But the fight to get innovation introduced is really a problem, and it is a problem for all of us, for all changes. This is the fairly standard way of reducing the amount of energy because of the proper blinds on the hospitals. This is the children's bit of the Big Eye Hospital in London. Again, here we've got the works of art, if you choose to call it that, on the outside as well as the inside. Now, obviously, the other really big one on the list is reducing the risks of hospital-acquired infections. And the Department of Health has focused particularly on policies. And the first one, which are all very sensible, the first one is introducing new posts and new roles for infection control officers for all healthcare buildings. And this means that there are a lot of people who now have this responsibility, not all of whom have been properly trained or experienced. The reinforcing the importance of hand washing and the use of the gels, that has been imported into every hospital across the country. An increased emphasis on improved quality of daily cleaning, and this is quite an issue in the UK because on the whole the hospitals do not employ the cleaners themselves. They don't directly control them. It's a contractual basis on the people who own the building are responsible for the cleaning and various other maintenance things. And then there's the introduction of regular deep cleaning programs in hospitals. Now it has to be said that actually the combination of all those things have given a heightened awareness, have certainly made the public more aware, certainly made visitors more aware. And there are these lovely stories of children in hospitals saying to the doctor when he walks to the bed, please go and wash your hands before you touch me. So it's obviously been penetrated through everybody. And there has been a reduction in the number of cases, not dramatic, but some. Now, whereas the designers are obviously not focusing on policies so much as on the building. Now, it's been mentioned, of course, but air management, the water supplies, the storage and the drainage are all very important. And we have very good standards in the UK. They're very well explained in terms of the engineering documents and guidance. And so it's obviously important that they all adhere to it. And good practice is pretty well explained, and I think on the whole is pretty well implemented. Designers are having a bit of trouble trying to make sure that into the buildings there is enough space put in for the storage of equipment. And when that fails, of course, it means we have equipment standing in the corridors, which is a risk in lots of ways. We have equipment standing in the corners of wards. Sometimes we have equipment even stacked up in bits of the clean utility room. So space being required for storage is one of the things that we've all been trying to work for. Obviously, proper places, space to do proper cleaning of equipment and furniture. And enough space is needed in all rooms for them to be properly cleaned. Now, the reason that there's such a focus on this is because the private finance initiative, which is our main way of procuring hospitals at the moment, actually is always trying to reduce the size of the footprint of the hospital because it saves money or makes more profit, whichever way you look at it. And so some of these really key bits of storage and cleaning spaces are really quite hard to get in to the right level. Now, obviously, another thing that we're very concerned with is the importance of detailing furniture and fittings, which are easy to clean and obviously avoid creating places where microbes can lodge and increase. Now, then we've got the bonus of copper. Yes, I want to talk a little bit about the current dilemmas which have yet to be resolved. And one of the ones is that when we've been, until we were made aware of the copper, benefits of the copper introduction, was we were very much arguing for eliminating touch items and replacing them with non-touch items, such as you don't touch a tap, it comes without you doing it. You don't open the door opens automatically. And so I think there is a question mark here as to what the pros and cons are of actually going for non-touch items, so that they actually don't become places which can actually transmit the infections, or whether there actually are more benefits to have more copper in the hospital, literally, and to not worry about the non-touch. And I hope some people will actually give me some response to that. Then there is this question of aesthetics versus functionality. Now, there is a tremendous emphasis, as I think you might have grasped from the pictures, that people are trying to make the interiors of these hospitals look very nice, very modern, generally photogenic, a little bit of architectural ego, I'm afraid, around. And they would expect, and the clients who've been wanting to have a hospital that looks like that they can feel very proud of and very happy in. If we're going to introduce new pieces of ironmongery or anything else, it's going to need to, I believe it's going to need to fit into the actual general design approach, which is not necessarily the same thing as reproducing existing door handles, taps, whatever. They may not seem appropriate. The sort of things people are looking for are the things you see in the kitchen shops and in the bathroom shops, really beautiful pieces of sculpture in terms of some of the taps and things like that. So I think aesthetics is actually going to be an important component in getting some of these things into the hospitals. Just offering the functionality may not be enough. Then we have another issue. It's our issue. I don't know that it's yours, but the question is, who should be specifying the materials? Because at some point, somebody specifies whether something is stainless steel or copper or something else. And if the clients, that's our project teams from the hospitals, from the hospital trusts, if they write in their brief what they want is this material, then that's what they will get. If they don't write it in, and they just have expressions like to meet the requirements to reduce hospital-acquired infections, then the chances are somebody else down the line will make that decision. If you're lucky, it's the architects. If you're not lucky, it will be the builders. And again, there is this intention, or not intention. People have different motives. The people who are building the hospitals are actually interested in building them for a profit and to get the next one as well. So this whole question of who actually should be specifying it is worth debating. And obviously, architects have the feeling that the architects are really in quite a good place, but the architects need quite a lot of education before they can properly introduce the copper as the new implement. Now, the next one is the reluctance to change current practices despite the potential benefits to patients. And it is quite shocking. I went to visit the example up in Sullyoak, and the cleaning women had made it very clear. They made it clear to Mark beforehand, but they made it very clear to me that They didn't like the copper because it doesn't look clean, and they can't see it. They can't see it looks clean, and therefore they are not happy with it. Now, to all of us, that seems quite extraordinary, because it's beneficial, this. They know perfectly well it is beneficial in terms of killing off microbes, but they still were standing, in this position, which was they didn't like it, which is an extraordinary in some ways, and I suppose not so extraordinary in other ways, because there is no visible evidence to people who are cleaning or walking around or whatever that this is cleaner and better and safer. But it has to be addressed somehow. I have a feeling it would be quite nice if these measures that were taken in the morning and the evening, if those figures were put up over certain items, maybe people would begin to understand it. But it seems to me that if they can't see a benefit, they don't appreciate the benefit. So I think that's something that's got to be addressed quite carefully. This other dilemma that is yet to be resolved is single beds or multi-bedrooms. Now, before the HAIs were a terrible issue, which they are, there were tremendous benefits in the multi-bedded rooms, and a lot of the research and studies had shown that. Probably the most important is that the nurses can have better observation of all of the patients, and that is a very important thing. And as soon as you start putting people in single rooms, you either treble the number of nurses, which financially is unlikely, or you actually have less good observation. And and also the people in the multi-bedrooms, they actually have some life going on around them. They have social interaction, and there was one particular survey that I did in a hospital where there were 3 completely different ward types, and we had designed the interview to be 20 minutes. When we went into a large multi-bedded room, like the one up here, it took the 20 minutes. Sat down next to them, had a conversation, private because it was so big. They told us what they wanted to say. Then we went up to then when you go to the 4-bedded room or the 6-bedded room, the interviews took about 6 minutes because everything they were going to say was going to be heard by the other people in the room. So the lack of privacy, there was no lack of privacy. So those interviews were very short, and obviously the nurses said they had exactly the same problem of communicating with those people because there was, the small group gave no privacy. And then when we went into single rooms, we were lucky if we came out after 45 or 50 minutes, because the people in single rooms were so pleased to have somebody to talk to and something to respond to that they were reluctant to let us go. Now, because of all those things, I would have advocated the benefits of big rooms, big wards for those reasons. But now, because of the infection issue, I think it's very difficult. I think it's very difficult not to say the single rooms must be more important. But we haven't got any evidence yet, and nor has anybody, that the fewer people are getting the infections because they're in single rooms. That data is just not available, and I don't think it's going to be available for a long time. So, it reduces the risk unduly, and the hospitals are busy wondering what percentage. Everybody's saying 100% single rooms, and then all the issues that you can imagine that go with it follow on from that. So that really is a tricky one. And really, the thing that I want to focus on is to say that how can we get the benefits that we now know that the copper can give in reducing the risk of infections. How can we get this into our hospitals as quickly as possible, rather than taking years and years? Now, obviously, it is essential to communicate the benefits to the key people, and they would be identified, I suppose, as the clients. And if the clients understand that, they could put them in the brief, and then that's what they'd get. The designers need to be brought up to scratch. The constructors tricky if they think it's more expensive and they're not going to get the benefits from it, but nevertheless, in principle, they should wish to do that. And the users. And given that it was the public who actually set the other standards of what they required, the things that mattered to them before, I have a feeling that perhaps the public are the people that we should be focusing on, because if they could get the Department of Health to come in with the new design policies and no smells of hospitals and lots of outdoor spaces, if they could get that over to them, I would hope they could get across that they want to have the benefits of copper in their hospitals. So that's one of them. But equally, they can't buy them. They can't even request them if they don't exist. So, of course, the next step is to make sure that they get made and who's going to make them. But it is essential that they are there to be purchased, so somebody has to invest in this, and I know it's not my problem, but there's no point in me telling people to do it if there isn't a product out there that they can go and purchase. But I'm also absolutely sure that they've got to be fashionable for them also to be likely to be sought after. And so I think the next steps are to try and make sure that we can discuss and try and work out how we can best do these, because it is silly. There is nothing difficult in installing any of these into hospitals. Nothing's having to be knocked down, nothing's having to be, rethought. It's just simple replacements, which really in a hospital is not very disruptive. So I just hope that that's what we will achieve. Thank you.
Good afternoon, ladies and gentlemen. My name is Mark Turr. About 2 years ago, I was tasked with implementing the fitting out of the ward in Selly Oak for the clinical trial, and I hope today to share with you a little bit of the experience that I've gained during that period with regards to the pros and cons of the approach that we took and the ease in which the hospital ward was fitted out. This is the basis of my presentation, why copper? It's not quite as simple an answer as you might expect. I know we've heard about copper for the last few hours, but there's more to it than that. Which components should we consider specifically, and some manufacturing guidelines? As Anne alluded to in the previous discussion, that's quite important. We should be looking at how we make these things. There are a few little tricks for manufacturers. And of course the future. Where do we go in the future? There's one step, creating a trial in a ward using perhaps existing designs, but something a little bit more radical perhaps should be thought about for the future. So just to make this absolutely clear, when we say copper, we're actually using that as a method of shorthand, an abbreviation. And we're talking about the whole family of copper alloys. Anything that has 60 or 65% copper in is going to be effective, more or less. And there's a whole range of copper alloys available to the manufacturer, a whole family, as we call them. They each have their own particular characteristics. They can provide different colours, different strengths. They can be more or less castable, but there is one member of the family at least for your specific application. But ultimately copper is the active component here. And there may be either synergistic or anti-synergistic effects from some of the other elements present: tin, aluminium, silicon, some of these that I've mentioned in this list. And a lot of data is already available, but I'm sure that more needs to be generated because that always seems to be the way. So copper is shorthand for brass, for bronze, for nickel-silver, and for cupro-nickel or copper-nickel alloys. Generally, as a guideline, the more copper you have, the more antimicrobial it will be. And these abbreviations I'm using here in this presentation are ISO abbreviations. They're generally recognized throughout Europe, not so recognizable in the USA, but we can still convert to USA specifications. CuDHP is what copper plumbing tube is made from, probably the largest single volume copper product manufactured. And what I'm saying here is generally that's better than a product with 8% tin in it. It's got more copper, it's going to be more effective. We've seen those graphs already. They indicate that if you have an extra alloying element in there, you possibly are reducing the efficacy of the copper. Similarly, copper with 10% of zinc in it, which is a brass. In the UK, we would call that a gilding metal. Elsewhere in Europe, we might use trade names like tombac, etc. Very well known amongst the manufacturers. But that's going to be more effective than a product with a 30% zinc in it. And again, similarly, 90-10 copper nickel, we saw some very impressive graphs this morning, is going to be better than a 30% nickel, copper-nickel alloy. But again, copper is the active ingredient, and that's the key thing, and that's the message that you need to carry. We've looked at the mechanisms, we're pretty clued up as to what some of the mechanisms might be, but in terms of practicality, the more copper you have, the better it is. This is an illustrative slide to show the different colours available. Anne talked about the exciting possibilities for copper as an architectural material. And certainly exteriors of buildings are clad with copper alloys. Not just the copper roofs that you might see that have gone green over the years. We don't have the same kind of pollution these days, so that's less of a problem. And in fact, a lot of architects use a specially pre-patinated green copper alloy for their roofs, so that has that instant aged effect. But various shades of brown, gold, right through to nickel silvers and high nickel copper nickel alloys, which are, to a layman, virtually indistinguishable to aluminium or stainless steel. But again, take this message, it's the copper that's active. The more copper you have, the better it is. So these are the products that we identified for the Selly-Oak trial. We did a qualitative assessment of those components which were frequently touched by nurses, patients, visitors. And we then reviewed them and decided that some of them we really couldn't do anything about. We couldn't, for example, very easily replace the metal binding at the top of a hanging file where the patient notes might be. Still regularly used in the hospital, and it has a painted steel top. If we were going to manufacture 10,000, it would be easy, but we were only going to manufacture perhaps 20, and that's a bit of a difficult manufacturing task. So we disposed of a few of these items as being impractical. Desirable, but impractical. We ended up with door handles and the push plates that work on the opposite side of a door handle. What's called a turn and release, etc. And I'll show you some pictures of these if you don't recognize the product. Most of these items on this list are already standard industrial products, often made in copper alloys anyway. But because of the fashion of the time, they're often chromium plated, so that the efficacy has been hidden away. I was looking at these water jugs on the tables. They look nice and shiny. I would not bet my reputation on it, but I would probably bet somebody €5 that that's actually a bronze or a copper product that's been chromium plated. It's beautifully fabricated into a very functional product. And copper's been used for many, many years for lots of different reasons. We know it conducts electricity, we know it conducts temperature very effectively, but it's also very fabricable. You can turn it into different shapes. And that's one reason why plumbing fitments, which are fairly complex components with a lot of machining, etc., that's why they're made in copper now. We've just forgotten that little secret that we knew 6,000 years ago, that they're antimicrobial. So as I said, here's some photographs of the products on the ward. Door handles, in this case made in a copper tin alloy. There are other door handles on the ward that are made in a copper zinc, a brass. Very aesthetically pleasing. The push plates on the opposite side of the doors have all been manufactured in copper, pure copper, apart from the main entrance doors, which are manufactured in a yellow brass. A turn and release is the term that architects use for an entrance system that can be released from the outside. So it's typical that you might find this in a toilet cubicle. So that if somebody becomes ill or accidentally locks themselves in, you can actually gain access from outside. These were manufactured again in a copper tin alloy, phosphor bronze. That top example is a phosphor bronze handle on a phosphor bronze backplate. Quite a substantial component and relatively modern looking actually, but you know, there could be strides made to improve design. That's actually very easy to clean. There are no corners, there are no grooves, there is nothing too fancy in the design. It's quite pleasing. And here is an example of brass grab rails, which were actually one of the more easily replaced items on the ward. The fabricator, who normally makes these in painted steel, was donated some brass tube by an understanding supplier, and they put them on their equipment and they bent them and they fitted first time, and they've been up on the ward now for the best part of 12 months. I think that photograph's probably after they've been in situ for certainly 6 months and probably 9 months. So the fear of corrosion and the product going green is not really evident so far on this trial. Again, we've got taps or faucets. The majority of taps in that hospital were already being manufactured in brass, but they were chromium plated. In a lot of cases, that chrome plate was being worn off because of the fairly aggressive chemicals that were being used to clean them. So chrome plate, which is notoriously porous if it's not applied correctly, was actually corroding away and not looking very nice in some cases. We've also managed to find toilet seats, some more grab rails here, a bit more complicated. The toilet seat was a coating. Because we were coating a plastic substrate, we found it much easier to go to a sprayed composite coating. There are some issues regarding how strong that is, how it will stand up to the wear and tear in a hospital. There's a lot of damage in hospitals through trolleys being moved around and so on. So designs need to be robust as well. They need to stand up to the typical hospital environment. Switches and sockets. One of the earlier speakers mentioned that the light switch was actually an identified touch and contamination and cross-infection point in one of the studies they carried out. We were very lucky. This was actually one of the bigger manufacturers that make this sort of product by the thousand right now. They specialize in metal components, but of course, most of their components are lacquered or plated with either nickel or chromium, or they'll use stainless steel because that's the fashion and that's what's being called for. These show brass components, but they were able to use exactly the same tooling for the copper and the bronze that they used to replace items on the ward. Bed tabletops. We don't have a similar situation in the UK. We don't use our bed rails as much as they appear to do in the USA. They are there fitted on the beds, but they're just not used because of the job of lifting them up, putting them into place, taking them down when you want to move a patient out. In our ward in particular, there was no danger that a patient would fall out of bed. They weren't that ill and they weren't that mobile. At least that's my understanding. So in fact, the bed table has become one of the focus items for replacement because it gets a lot of traffic. The patient will touch it, they will eat their food there, the nurses deliver medicines there. They actually sometimes use that to put dressings on when they're changing dressings. So it's quite a serious infection point, contamination point. And this is one of the more difficult components to change because the original manufacturer just wasn't interested in doing anything. Again, we tended to work with local entrepreneurial manufacturers because they had the flexibility to cope with small production runs, whereas bigger production runs were a bit of a problem. If we went along to the OEM, the original manufacturer, and said, make me 1,000 tables with a copper top, fine, no problem. But actually, I'm going to ask for about 10, and then that becomes a little bit too specialised for them. We found a coppersmith that's in a completely different business area was very happy to do this for us. So we're very pleased to have this on board. The other nice thing about this sort of product is that it's very portable. So once we've done our trials, we can move it into a different ward and give it a different type of exposure to different types of infections, maybe in the MRSA control ward or a general ward where there's no special cleaning and so on. It's standing up very well to hospital use, I might add. Now, one thing that those of you who are a little bit more awake after lunch might have noticed is that as I've gone through these slides, I've been adding to the bottom of them. Because every time I go back into the hospital, they say, what about this? Can we get one of those made? Or, look, this is a problem here. And the key is to continue to be flexible and be prepared if you're running any kind of trial, having any kind of dialogue with the healthcare environment, to go in and listen and talk to them. Talk to the cleaners, find out what they don't like. Talk to the nursing staff. Be prepared for change. It's a real-life, dynamic situation. Now, these are my key guidelines for manufacturers. And the first one is nominate a project leader, a champion, a project champion. That individual is very, very important. Now, I've been the project champion for the CDA, but I've tried to maintain one single point of contact in every other supplier that I visited. And that's because I don't have to go around the same story again. One of our suppliers, their personnel has changed, they've nominated different people. We're on to our fourth name in 12 months. And frankly, I've given up talking to them because it's too painful to keep doing that. So please nominate a champion. They can become informed, they can make decisions, they can collate the information, whether it's from the various CDA websites, it's from all the references that we've been given. They can liaise with the suppliers, the clients. Doesn't matter where you are in the supply chain, you need to have a champion. Choice of alloy. Very often there's actually no choice. Most of the lever taps on our ward are already cast in brass. It wasn't a difficult decision to search out a manufacturer that made these and would just not put the nickel plate on or not put the chromium plate on. Pull handles on doors. Most of them in our ward were aluminium, anodized aluminium, a few stainless steel ones. The more complicated ones were brass because brass is such a great alloy to cast. But it was chromium plated. So, currently fabricated in bronze, but lacquered. That was the story for a pull handle. If you have got a choice, you should think about how you're going to manufacture the product. Are you going to bend it? Are you going to weld it? Are you going to braze it? Are you going to make it by casting? So the fabrication process comes along at the same time as how strong does it need to be? Are there standards that require special testing? Door handles have to withstand certain strength criteria. It's great if you already make something in a brass. You know it's going to work anyway. But if you currently manufacture it in aluminium, you may not have the engineering expertise to consider a different material. Now, those of us who are well versed in these materials know that generally brass is stronger than aluminium. It shouldn't be a problem. But I know from painful experience that the depth of engineering in most manufacturing businesses is painfully small. So you might need to hold people's hands as you go through this process. And availability. If you're going to manufacture something from sheet material, Go and get something that you can get from a stockist. Start there. You might want to change it later on, but you can perhaps get a 70-30 brass much more easily than you can get a 90-10 brass, for example. That might be your ideal, but availability is a key issue. So we talked a little bit about strength. You can gain strength by choosing the correct alloy. You can gain strength by choosing a different thickness of material if you're going to fabricate something. And in terms of the copper alloys, most of them gain strength by cold work. You know, if you get a Coke can and you twist it when it's empty, of course, twist and twist, eventually it breaks. That's work hardening. So you're making it so hard it becomes brittle. It's the same principle with the copper alloys. There are some heat-treatable alloys and they should be considered, but only when you're talking to a very experienced and technically knowledgeable supplier. What's your fabrication process? I touched on that earlier. Are you going to bend it? Are you going to join it? Think about adhesive joining as opposed to welding. Welding is not that easy with copper alloys. Brazing is great, but in some industries it's a lost art. People have forgotten how to do it. Most plumbers know how to do it, but even those are used to push fits now. And machining. Brass is used, it's specified, it's used in very complicated components because it's easy to machine. That should be one of the key selling points. You could probably reduce your manufacturing time over a stainless steel tap by 80%. That's time on a machine. That's got to have a cost implication. Don't just get carried away with stainless steel because it's the material of the moment. And availability, again, talk to your supplier. What is in stock? Put some pressure on them to provide you with technical information. If you don't have the expertise, if you can't find a partner that has the expertise, your supplier or the supplier to them should be able to have some dialogue with you. And forget about the cost. Everybody brings up the cost of copper. If you're talking about a fabricated component, it might be 10, it might be 20% of the cost of the whole component, but in fact, the majority of the cost in most of these fitted on the door, on the ward components is down to labour. A tap replacement made in a brass that isn't nickel plated or chromium plated should be a bit cheaper. By the time it actually gets onto the ward and an engineer has taken off the old one and put the new one on, it's the same price. This is really a detail. So think about value, not cost. Just to go over once again the manufacturing guidelines, don't forget to nominate a project leader. Your champion, that is a fundamental goal. Find one. If you are tasked with doing this for your hospital or your healthcare environment, whoever you talk to, make sure that they are going to be talking to you next week, next month, next year. Choose or modify a design that you already make, like the taps. Those taps that we've installed in our ward are an existing design. There's nothing new about them. Long term, think differently, think positive. Think about a new design perhaps, but concentrate on things you do right now. What about the finish? Polished or brushed? I think the truth is that we haven't done enough work on those aspects. Brushed finishes are very attractive. They can harbour dirt and grime in those little scratches as we've seen on slides. But in fact, on the copper alloys, if there's a germ in there, it's dead. It doesn't matter that it's in there. If it's stainless steel, it's in there, you've got a problem. But the majority of stainless steel and aluminium that's used in architectural fitments is brushed. So the jury is out on that. And critically, when you're discussing or you're specifying a component, we want no finishing wax, no lacquers, no plating. Some polishes, some silicon polishes leave a residue. They will affect the efficacy of the copper. So we don't want any of that. Bare, clean, nothing extra. Again, manufacture standard items as much as possible, make as few changes in the short term as possible. And in terms of a ward, we found it was important to minimise any upheaval, any changes on the ward. Try and work with the systems they already have. And that's caused us some problems. For example, the soap system has changed from an on-the-wall dispenser, which was quite a robust, solid component, to a much more simple push-button dispenser. And for very good reasons, that is a dynamic part of the hospital environment. But now we've had to change our philosophy as to how we cope with that slightly different component. And again, key contacts. When you're talking to hospitals, healthcare environments, gyms, wherever you're going to get some of this work done, whether it's in your own, you want some key contacts. And they need to be all through the organisation you're talking to, not just the professors, not just the surgeons. Talk to the nurses, talk to the cleaners, talk to the guys that do the maintenance. And install stuff as soon as possible, because they'll change their mind. I said you have to be aware that it's a dynamic situation. If you go back in 6 months' time and say, here, I've got a tap, they say, well, we changed that. We want one of these now. It's got to fit there. You've got to go back to your manufacturer. Do it as soon as you possibly can. And for the future, prepare designs. Think about the future. Anne's dead right. We've got an opportunity with the copper products to be very innovative in terms of designs and meet all the requirements of a low infection environment. They're very amenable to being worked. They're a manufacturer's dream very often. Think about your pricing. Is it really going to be cheaper when you sell your tap without chromium plating? Prepare your pricing. Get your head around these things. Get your marketing manager to think about these things. And if you are approached as a manufacturer, and this is the difficulty we have currently, is be prepared to supply. Don't sit back and say, well, yeah, we gave you some taps for the trial. We don't know if that's really our market. Be ready, be prepared. Price them up, think about designs, be proactive as much as possible, because for sure, this is a slow revolution, but it will be a revolution. In 50 years' time, we'll look back at this conference and say that was the turning point. Thank you for your time.